All right, next we're going to look at another example. And this example is contextless, meaning we're not talking about really anything applied. This is just strictly numbers here. Um, but we're going to use this notation for a normal distribution of a random variable. So this says that x is normally distributed with a mean of 5 and a standard deviation of 6. So again, a mean of 5 and a standard deviation of 6. Now, suppose the value of x that we're interested in is equal to 17. Create overlapping graphs of the normal distribution of the population and the standardized normal distribution. And then part B, find the z-score of x equals 17 and label its position on the graph. So what I mean by overlapping graphs is in the previous example, I took the normal distribution and the standard normal distribution and I put them side by side. But now instead of putting them side by side, let's overlay them on top of each other. Okay, that's what I mean by overlapping graphs. So if you want to, go ahead and pause now and see if you can sketch this on your own, and then resume and see if your sketch matches mine. Okay, so let's do a quick sketch of this. Let me see how much room I got. Okay, so I'm gonna leave myself a bit of room here. So I'm gonna use up a lot of horizontal space. So I'm gonna draw my normal distribution, which is bell-shaped and symmetrical, maybe something like that. And we have a mean of 5. So let's see here. So we have a mean of 5 and a standard deviation of 6. So if we add 6 to 5, it's going to give us 11. And if we add 6 again, that'll give us 17. And so this is going to be the mean plus 1 standard deviation. This is the mean plus 2 standard deviations. And if I add 6 again, this is going to give me 23, which is the mean plus 3 standard deviations. Now let's go in the opposite direction. And now instead of adding 6, if I subtract 6, that'll get me to -1. So this is the mean minus 1 standard deviation. If I subtract 6 again, that's going to give me -7. So this is the mean minus 2 standard deviations. And if I subtract 6 again, it's going to be -13. So this is the mean minus 3 standard deviations. So you can see I've iteratively gone above the mean in multiples of standard deviations, and I've gone below the mean in multiples of standard deviations. Now let's put this on a z-scale. So here the mean was 5. Now on a z-scale, let me use a different color for that. So on a z-scale, oh my goodness. Okay, a z-scale, the center is going to be a z-score of 0. And this will be +1, +2, +3, -1, -2, -3. So the reason why it's instructive to overlay the normal distribution and the standardized normal distribution is notice where this +1 comes from. It comes from the number of standard deviations above the mean. Look at where this +2 comes from. It comes from the number of standard deviations above the mean. And look where this positive 3 comes from. It comes from 3 standard deviations above the mean. And likewise, when we go the other direction, where this -1 comes from 1 standard deviation below the mean. -2, 2 standard deviations below the mean. -3, 3 standard deviations below the mean. All right. Now, so this is, drawing the normal and the standardized normal kind of on top of each other. So that's part A. Part B is to find the z-score of x equals 17. So let's find 17. 17 is right here. Well, guess what? That's going to be an exact z-score of +2. Okay? But let's confirm that. So our z-score is going to be equal to x minus mu divided by sigma. Our value of x is 17 minus the mean, which is 5, divided by our standard deviation, which was 6. And so 17 minus 5 is 12, divided by 6, which is +2. So when x equals 17, the z-score when x is 17 is equal to +2. So we calculated this value algebraically using this relationship, using this relation between z-score and a value of x. And we also determined it graphically using the superpositioning of the normal distribution and the standard normal distribution. Okay, let me know if you have any questions.